Hello everyone, myself Surendra Kumar from the Department of Electronics and Communication and the College of Engineering. Today I am here to deliver a lecture about the transistor biasing circuit. This is a very important topic for electronics and communication engineering students. And I hope you will enjoy this session, and after finishing this session, you will be able to use your transistor in a circuit with its biasing technique. So let's talk about first of all, what is the meaning of biasing? In a biasing circuit, we will provide the DC supply to work a transistor in that way to get less output. Right. Okay. This is the first slide. You can see here the output characteristics of transistor, which is drawn between collector current and DC voltage. So here the biasing is the application of external DC supply to stabilize the fixed level of current and voltage. Here, this is the Q point, and for this Q point, we have a fixed value of this DC, and for this DC, we have corresponding current IC. Here it is current. So to stabilize this Q point and this active result of the characteristics, we use some basic biasing circuits. So this is our main aim to stabilize this Q point and the active result. Need of biasing circuit. The first aim use of biasing circuit is to establish operating point, which is also known as Q point of transistor, in the center of active region of the characteristics. To stabilize, second one, collector current IC against temperature variation. If there is a change in temperature or physical conditions are being changed, so the operating point and Q point of transistor should be minimum effective. So it should be stabilized against any variation in the temperature. To make the operating point independent of transistor, so that it does not fit when a transistor is left. Actually, if we replace a transistor with the same number, so it is not possible to meet all the characteristics of a transistor. For example, beta is equal to 100, if we are choosing. So it is not fixed that the new one transistor will have the exact value of beta. It may be 100.1 or 99.9. So for this very small variation, we will have some kind of change in terms of collector current, and this collector current change definitely will affect the operating point of transistor. To understand this phenomenon, let's see this diagram, in which you can understand better if this Q point or operating point is not fixed in the middle. So what kind of distortion we will have in the output waveform? In this first diagram, we can see this Q point is shifted towards the cutoff region, and at the output, we don't have this part of waveform. So we can say the output waveform is distorted. And the same way, if this Q point is shifted towards upward, then we will know this part of the waveform. Here, if operating point is fixed in the center, and my input signal is quite large and exceeding below the point and crossing this saturation level upper side. So we will have this type of output waveform. It is clipped positive side and negative side. So we don't want this type of distorted output waveform. To avoid this kind of distortion, we use some biasing circuits to avoid this kind of distortion. These are the some types of biasing circuit. First one, this is very basic circuit, fixed bias circuit. Second one is collector feedback circuit. Third one, fixed bias circuit with ammeter resistor. And fourth one is voltage divider biasing circuit. So let's talk about the first one, fixed bias circuit. It is known as fixed bias circuit because the voltage at this phase is decided by this fixed value of RB, and the collector voltage is decided by the value of RC. So, in this analysis of fixed bias circuit, we apply KVL from the base emitter loop. We have this VCC minus IB, RB minus VB is equal to 0. So IB will be equal to VCC minus VB upon RB. This is the simple calculation in terms of to find out the phase current. Here, collector emitter loop, or we can say apply KVL in the outer loop. We have VCC minus ICRC minus VC equal to 0. This is simple KVL equation we have applied in outer section. Here VC is equal to VCC minus ICRC. And now, if we have IB base current, with the help of this base current, we can find out IC, which is equal to beta. So, to determine the operating current of transistor, which is the first requirement of our circuit, we need to find out base current, collector current, and collecting emitter voltage. So now we have all these three values of transistor. So it will help you find out or determine the operating on that transistor. So this is our first thing. Now, to check the stability factor of this fixed bias circuit, which is given by this formula beta plus 1 minus beta, and DIB over here. So this is the change in base current with respect to collector current. So for every circuit, our focus will be to find out this value of IB with respect to IC. So if you put this value in this formula, we will have a stability factor. And most important thing about the stability factor, more value of stability means poor stability. So stability factor and stability moves in opposite direction. Here you can see in this diagram IB base current, which is equal to VCC minus VB and RB. It is totally independent of collector current IC. So if we differentiate with respect to collector current, the value will be 0. So DIB or DC is equal to 0. Here stability factor, if we put the value here, so we will have only beta plus 1. It is quite large, and the value of collector current will be changing by this factor beta plus 1. Now, collector feedback, this is the second one, collector feedback circuit. Here we are providing a feedback connection from the collector to the base circuit for this base resistor. So now with this load resistor, or you can say collector resistor, both the currents simultaneously flowing through this branch, IC and ID. So by applying again the KVL in input section, ID plus IC, RL plus ID, RD plus VB is equal to VCC, and finally we will have ID current VCC minus VB minus IC RL upon RL plus RB. In this expression, so this is very, very important now in this second biasing circuit. The base current depends on collector current because of this feedback part. Now, if we have base current, simply we can find out collector current IC, that is beta IC, very basic current collector current equation. Now, if you put the base current value in this formula, we can find out this collector current. Now, by applying KVL in outer section, we will have this KVL equations. VCC minus ICRC minus VC minus IERE, and finally we will have the voltage across collector and emitter terminal, which is VCC minus IC in bracket RL plus RE. So again, we are going to check the stability. Is it improved as we compare with the fixed biasing circuit? So here we can see the value of DIV or DC is not 0, it is equal to minus RL upon RL plus RB. Now, putting this value in this stability factor, we will have 1 plus beta upon 1 plus beta in bracket RL upon RL plus RB. So definitely we have a large value in denominator, and overall effect will be there, that stability factor will go down. So if stability factor is going to down, definitely there will be an improvement in the stability of collector to base feedback biasing circuit. Advantage, this value of stability factor is smaller than 1 plus beta. Already I have discussed just before, which is obtained for fixed biasing circuit, because this is an improvement in the stability. So we can say this circuit is better as compared to fixed bias circuit. What is the disadvantage of this circuit? This circuit provides a negative feedback which reduces the gain of amplifier. So the increased stability of the collector to base bias circuit is obtained at the cost of AC voltage gain, which is not desired. Actually, we are using this biasing circuit for amplification purpose in amplifier circuit. So if we are getting a loss in voltage gain, so it is not a good fact. So we will use this circuit. Next, third circuit is fixed bias circuit with emitter resistor. So we have made some modification in the previous. You can say first circuit, which is a fixed bias circuit. You can say the above side R3 and RB are same as it was in fixed bias circuit. Here the new resistor is connected with the emitter resistor. Now by applying KVL for the input bit of this circuit, we have VCC minus IDRB minus VB minus IDR is equal to 0, or IB is almost equal to VCC minus IDR is upon RB. We are neglecting VB here, which is very, very less than as compared to VCC. Now apply output loop equation, which is VCC minus ICR in VCE minus IER. Again, it can be written for VCE, which is equal to VCC minus IC RC plus R. So here also we have two important values, IB, IC, and VC, which are required to determine the operating point of transistor. This is the stability check for the passive circuit with amateur resistor. We can say with the help of base current. See this base current, we have here ammeter current, and we know what is the relation about ammeter current and collector current. Both are almost equal. So we can say the base current depends on ammeter current as well as collector current. So the dependency of collecting current, dependency of base current on collector current makes advantage of this circuit. How it helps, you can see in the next diagram. You can say this temperature is going to increase, that will affect the ICDO, which is the leakage current. Definitely it will go high, and this will increase the leakage current from an ammeter configuration, which is ICDO. And ICO is a part of collector current, so our collector current will also increase. So this collector current and ammeter current both are almost equal. There is a very minor change. So here IE and RE will also increase. And if this IE RE factor increases, definitely the base current increases. This base current will counterbalance this increment in collector current, because IC is equal to beta I. If base current is going to decrease, definitely there will be a decrement in collector current. So you can see clearly with this diagram of the Transistor chart. As temperature increases, it affects the leakage current. Leakage current will affect the collector and ammeter current. Finally, base current will go down, and the collector current will be decreased. So we can see the increment in collector current is counterbalanced by using the ammeter resistor. So it provides better stability as compared to fixed wire circuit. In case of transistor, it is replaced by another the same type of transistor. What kind of changes we see? Let's understand this effect with the help of this diagram. Here, VCC is given in terms of beta. We writing this period in the slides. So it is in terms of beta plus 1, IB, RE, and IB. We get it IB plus RB, sorry, RB plus IE, beta plus 1, it's going to be VCC minus VB. So the base current can be given as VCC minus VB, RB plus beta plus 1 RB. So you can say base current approximately equal to VCC RB plus beta RB. Here again we have neglected this VB voltage which is very, very small as compared to this. So, with the help of this base current equation, IB is equal to VCP upon RB plus beta RE. You can understand this diagram. As beta is going to increase, because collector current depends on beta, which is equal to beta IB. So collector current will also increase initial state, and then this collector current will affect this emitter current because both are almost equal. And again, we are getting a change, incremental change in IE RE. And if IE RE is going to increase, again, the base current is going to increase. It is already explained in the previous base current equation here. If IE RE is going to increase, definitely the base current will increase. So here the decrement in base current will decrease the collector. So the effect of beta also nullified by using this here. So let's check DC feedback disadvantages of this circuit. DC feedback through emitter resistor and the stabilization of Q current. AC feedback reduces the voltage gain at the amplifier, which is undeniable. So the same drawback is with this type of passive circuit. It also reduces the AC voltage gain, which is not desirable. Why this circuit is not used? Because in the previous slide we have this mathematical expression of IB parity, and IB it is VCP upon RB plus beta R. So as we know, I see the beta into IB, putting this base current value, we will have this mathematical expression. So now the collector current calculated as VCP upon RB plus R2 upon beta. The denominator can be independent of beta. You can say we want this denominator independent of beta. So the value of RE and value of RB. RB should be very low. If we make independent of beta, this denominator, and the value of RE should be very high. So denominator can be independent of beta for very high value of RE and very low value of base resistor, and both are impractical and going to increase the voltage. If we increase this RE, so it will increase the AC feedback. Again, we will have a decrement in voltage gain, which is not desirable. And here it will increase this RB, which provides the base voltage, which is equal to 0.7, quite low voltage. So if we decrease this base resistor, it will be destroyed. Both the things are impracticable, and that's why we don't use this circuit. And last one, very important, mostly used circuit, voltage divided by C circuit. Why we are following this voltage divided by C circuit? Because these two resistors R1 and R2 provides the voltage divided two here, because in this, if we assume that the base current is 0, neglecting this base current, so the same current will flow through this R1 and R2. So these two resistors will be considered as a series connection. So this circuit is called with the help of Thevenin equivalent circuit. Thevenin equivalent, we have here R1, R2. So the Thevenin equivalent resistance of this can be calculated if RTH is equal to R1 R2 upon R1 plus R1, and the voltage at this output terminal, or you can say across R2, will provide a terminal voltage. So this is the equivalent circuit of voltage divider for input side. Here we have terminal equivalent voltage and in series RTH, terminal equivalent resistance. Will provide that equivalent circuit for the voltage divider whole circuit. So now by applying KVL, we have here input side VTH minus IB RTH minus VB minus IB RTH and IB VTH minus VB upon RTH plus beta plus 1 RE. By solving the output collector ammeter load by KVL equation again, it's very simple. Every time we are writing the same equation, almost same equation for DC collector to ammeter voltage, which is CP minus RC plus R. Here we are considering that IP and IC are equal, because here we are taking only IC. We are not considering this IE. So we are assuming that IC and I is equal. Merits of this circuit: operating point is almost independent of beta variation. Operating point is stabilized against separately temperature, as we have seen in previous circuit. So the same type of advantage is provided by this circuit. Demerits: beta value is fixed for given transistor. This relation can be satisfied either by keeping R1 fairly large or making R1 R2 variable. So by having proper selection of R1 and R2, we will have a small value of this direct combination of R1 and R2. If RE of large value, the high VCC is necessary, and it will impact the overall voltage, AC voltage, which is not required. So we can overcome this AC feedback voltage by applying a capacitor in the parallel of this resistor. So AC as well as DC feedback exposed by RE, which reduces the AC voltage below that. DC feedback is good to stabilize the operating point, but the AC feedback, it is not required. That will decrease the overall voltage gain of transistor. So to avoid this, we will use the capacitor in parallel for RE. You see, this circuit is stability and merits will make it widely used for linear circuits. Summary: the Q point is the best point for operation of a transistor for given collector current. The purpose of biasing is to establish a stable operating point of Q point, you can say. The linear result of a transistor is the result of operation in the situation and cutoff. Out of all biasing circuits, potential divider circuit provides highest stability to operating point. So this is the summary of the previous lecture about transistor biasing circuit, and we have seen all basic circuit: fixed bias, collector feedback bias circuit, biasing with energy resistor, and voltage divider. The first one is never used in the circuits because the stability factor is very high, or stability is very good. Second and third provide much better stability, but there is a same drawback that it provides AC feedback. which reduce the voltage gain, AC voltage gain. So second and third also is not reduced, and finally we reduce the voltage divider, or we can say cell pass circuit to get the historical cycle. This is the complete amplifier circuit with the voltage divider, in which we have used biasing or we can say DC supply and AC signal. So here, this is the SAM bias or voltage divider circuit in this amplifier, and this capacitor is used to nullify the AC voltage that was developed at this amplifier. I hope you have enjoyed this lecture and can make better use of this lecture to understand the biases. Thank you.